Okay, so in this section, we are looking at standard normal calculations. So we're looking at a normal curve, the mound-shaped symmetric curve, that has been standardized. That means we've converted everything to z-scores, that the mean is 0, mu is 0, and sigma is 1. And the notation for a normal curve looks like this. It's n for normal, and then you always list out the mean and the standard deviation in parentheses like this. So, in the standard normal distribution, all observations have been converted to z-scores. There's 4 kinds of questions that you will see regarding standard normal calculations. The first one is, what proportion of observations are below a given z-score? So you can see we would shade to the left because numbers go lower to the left. So you're looking for that area under the curve that's left of a given z-score. Okay, so then you could be asked, what proportion of observations are above a given z-score? So we would shade to the right. You could be asked, what proportion of observations are between two z-scores? So they would tell you that, and you would find that area between the two values. And then lastly, they would give you the area, and you would have to work backwards to find the z-score that designated that area. So I'm going to show you how to do this. Now notice that empirical rule is not going to work here because the z-scores can be any value. They don't have to be 1, 2, or 3. They could be any decimal value. So we have to have another tool, and you do have another tool in your calculators. Alright, so here's some example problems just to kind of get you familiar with this. Find the proportion of observations less than a z-score of 0.54. So I draw my normal distribution. Remember, the center is always 0, and 0.54 is positive, so it's above the center, so I would label some place above the center and label it 0.54. And the question says, find the proportion of observations less than that value. So I would shade my curve to the left, or less than, and then you will find in your calculators there is a function called the norm CDF. It is a table of values that have been calculated to find the area for every possible z-score out there. So you get there by doing second vars and then norm CDF, and it's going to come up with an output that looks like this. So these are the prompts that it's going to give you. The lower is what's the lower value of the shaded region? Now think of your horizontal axis as a number line. If you're going all the way to the left, that basically goes to negative infinity. So it could be negative infinity for a z-score. Now, we don't have that calculator button, so we just use negative 1 e to the 99. You could use negative 10,000. You could use any negative large number. It would be fine. But the default there is in there. Now, the upper is asking, what's the upper boundary of your shaded portion? Well, in this question, our upper boundary is 0.54. And then it asks me, what is the mu and what is the sigma? Well, it's standardized because I'm using z. My mu is always 0 and sigma is always 1. So when I put that in my calculator, I get a p-value, a proportion of 0.705. So let's look at B. Find the proportion of observations greater than z equals 1.12. Okay, 1.12 is positive, so again, it's going to be the right of center just a little. And greater than would mean I need to shade to the right. I'm looking for the area under the curve to the right of that z value. So in my calculator, my lower boundary this time is 1.12. The upper boundary, I could put in positive 1,000. I could put in positive 1 e to the 99. Whatever works. A very, very large positive number for my upper boundary because basically it's going to infinity. Mu is 0 because we're standardized, and sigma is 1 because we're standardized. When I put that in, I get a p-value of 0.131. On C, find the proportion of observations between a negative 1.06 and a positive 1.82. So I draw my curve, and I put those boundary lines in there and label them. Negative 1.06 is to the left of center, and obviously 1.82 is to the right because it's positive. But it's a between problem, so I'm shading between those two values. In my calculator, my lower boundary Where's the lower boundary of my shaded part? Negative 1.06. Upper boundary is 1.82. Again, z-scores, if you're dealing with z-scores, your mu is always 0, sigma is always 1. This gives me a p-value of 0.821. Alright, in part D, find the proportion of observations within 1.5 standard deviations from the mean. Okay, so I start with my normal curve. 1.5 standard deviations could mean below the mean and above the mean. So I have to consider a z-score of negative 1.5 and positive 1.5. So I'm looking for the area between the two. And so in my calculator, my lower boundary is going to be negative 1.5. My upper boundary is 1.5. Again, because I'm using z-scores, mu is always 0, sigma is always 1. So using my norm CDF function, I get a p-value or a proportion of 0.866. Now look at E. This is a little different. The distribution of test scores is approximately normal, and Joe scores in the 85th percentile. How many standard deviations above the mean did he score? So how many standard deviations above the mean? That means what's the z-score? Another way of saying what's the z-score? Because remember, z-score is the number of standard deviations away from the mean. So let's think through this. All right, there's my normal curve. It told me it's normal. He scored in the 85th percentile. Now, right in the center, the mean, because it's symmetric, is the 50th percentile. So 85th percentile is way above the mean. And the question is, okay, if the area over here on the right is 85%, he's right here where this line is. What is that z-score? How many standard deviations above the mean is that value? Well, you have to do this a little different. You're going to use a feature in your calculator. It's in the same menu, second bars, and you're going to do inverse norm. In that menu, this is what they ask you. They ask you, okay, what's the area under the curve you're looking for? Well, it's 0.85. And it's asking you, okay, if this is normal, so I'm looking for the z-score, mu is still 0, sigma is still 1. And in some calculators, you have this option of tail. Usually, it's left tail. And if you look at it, which tail is the area in this situation, it is the left tail. So just leave it as left. When you do that, it's going to give me a z-score of 1.036. So that would mean that 1.036 standard deviations above the mean is how well Joe did. Okay? All right, F. In a normal distribution, Q1 is how many standard deviations below the mean? Well, you got to remember what Q1 is from Chapter 1. That's the first quartile, or 25th. So here's my normal curve. If the middle is 50%, Q1 is the lower 25%. So ballpark it, this is that region of the curve. So how many standard deviations below the mean? Well, that would be what's the z-score there. So I'm going to have to use that inverse norm function again on my calculator. The area is 0.25. Mu is still 0, sigma is still 1. And the tail, we want the area at the left of my line, so it's the left tail. All right? Put that in there, and I get a negative 0.674. Or the way I would interpret this is say 0.674 standard deviations below the mean. All right? Now, when you do a normal calculation question, generally there's three things I'm looking for. First of all, you draw and label the curve. You state the distribution and identify the variables. Okay? You need to have there somewhere n and then the mean and the standard deviation. And all the examples I've done so far, these were just standardized curves where the mean was 1 and the sigma was 0. All right, no big deal, nothing changed there. But sometimes these change, and I'll model that for you here in a moment. Now, on the calculations, you need to show any work. If you're using calculator speak, like this norm CDF or inverse norm, you got to make sure you label your values with correct symbols, like mu and sigma. And then lastly, answer the dang question. Make sure you put it in context and you've answered the question that was asked. All right, so here's an example. In the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serves. Assume that the distribution of his serve speeds is normal, first serve speeds is normal, with a mean of 115 miles an hour and a standard deviation of 6. About what proportion of his serves would you expect to be slower than 103 miles per hour? All right, so first thing I want to do is draw my curve and label it. Label it N for normal, 115 is my mean, 6 is my standard deviation. Now, I need to convert this 103 value to the appropriate z-score. So that's the observation right here that I want. So I'm going to take 103, subtract the mean, and divide by the standard deviation of 6. When I do that, I get a z-score of -2. So then I need to draw that on my curve. It's definitely to the left of the mean, so there's z of -2. Now the question is, which way do I shade it? Well, look back at the question. It says slower than 103. So slower than would be less than. So I'm going to look for the area to the left. Now, in my calculator under normal CDF, my lower boundary is the -infinity, upper boundary is -2, the mean is 0, sigma is 1. The area that gives me is 0.023. Now, to answer that question in context, it would look like this. I would say about 0.023 of Nadal's first serves are slower than 103 miles per hour. Notice it's in context. Notice it's not just a naked answer of 0.023, but it has meaning. All right, same question, part B. It says, about what proportion of his first serves would you expect to exceed 120? So we're going to go through the same process. Draw the curve, label the values, and we need to calculate the z-score that goes with the observation. So I put in 120, I subtract the mean, and then I divide by the standard deviation. This gives me a positive z-score of 0.833. So that sits a little bit to the right of the mean. And I need to decide which way am I going to shade. Well, look back at the question. It says exceeds 120. So that should indicate in your mind that it is greater than 120. So I'm going to shade it to the right. And that helps me to identify my boundaries for my calculator. All right, so my lower boundary is 0.833. My upper boundary is positive 1,000. Positive infinity, but I put in 10,000. And then mu is 0, sigma is 1, again, because I'm using a z-score. All right, find the value, it's 0.202. So then to answer the question in context, I would say about 0.202 of Nadal's first serves are faster than 120 miles per hour. All right, so part C. What percent of Nadal's first serves are between 100 and 110 miles per hour? So same steps. Draw the curve, label the values, and we need to convert both of these boundaries to z-scores. So I'm going to do my calculation. So 100 minus 115 divided by 6 gives me a -2.5 z-score, which falls far to the left of the mean. Then I do the 110 value. It's still negative, but not as far from the center at -0.833. So it sits right here. Now, this is a between question, so I'm going to look for the area that falls between these two boundaries. So these are the two boundaries I'm going to use in my calculator. And you can see my lower boundary is -2.5, my upper boundary is -0.833. The mean is still 0, and sigma is still 1. It gives me a p-value of 0.196. So the correct interpretation of this answer would be that about 1.196 of Nadal's first serves are between 100 and 110 miles per hour. Part D. What's the fastest 30% of Nadal's first serves go at least what speed? So again, we draw the normal curve, label it, and then think about what's going on. 30% is an area under the curve, and it wants the fastest 30%. So fastest makes it fall on the right tail. Slowest would be on the left tail. But we want the fastest 30%. But they gave us an area, and we want to know what that speed is. But first we got to find what the z-score is that cuts off that area. So we're going to use our inverse norm feature in our calculator, put in the area of 0.3. Mu is 0, sigma is 1, and in this case I would choose the right tail. Now, if your calculator doesn't have this tail feature, it defaults to the left. So you always want to put the area to the left. So if this was a question, if its area was 0.3 and it's the highest or the fastest 30%, then the area that you would actually put in your calculator would be 0.70 because the whole thing is 100%. 30% is on the high end. That's what we want. 70% is on the low end. So you would put in 0.7 if you didn't have the tail feature. Now, that being said, I calculate a z-score of 0.524. That should make sense. It should be a positive value and above the mean. Now, I have to use that z-score to calculate the speed. Using my z-score formula, there's my z-score. It is the observation minus the mean divided by the standard deviation. Then I'm going to use algebra just to solve this. Multiply both sides by 6, get rid of the fraction, there it is, and then I'm going to solve for x. The final answer would be that the fastest of 30% of Nadal's first serves go at least 118.14 miles per hour. So you want to correctly interpret. Alright, last part. Part E. A different player has a standard deviation of 8 miles per hour on his first serve, and 20% of his serves go less than 100 miles per hour. If the distribution of his serve speeds is approximately normal, what is his average first serve speed? Alright, lots going on here. Different player, we don't have the same mean and standard deviation as before. In fact, we don't know the mean at all. So I know it's normal because they told me that. But when I label it, I leave mu there because I don't know what it is. But I know the standard deviation is 8. Then it says that 20% of his serves go less than 100 miles per hour. So I know that the 20% of area of 20% is less than this z value right here. Okay? So I need to find that z value. And again, if it's an area problem going to a z value, I'm going to use the inverse norm function. Notice I'm going to use left tail this time. Mu is still 0, sigma is still 1 because I'm looking for the z-score. It gives me a z-score of negative 0.842. And that will help me then find my mean. So I'm going to take that value and plug it into my z-score formula. So I have a z-score, I have the observation, and I have the standard deviation. This way I can solve for the mean. So if I multiply both sides by 8, I get this. Then I need to subtract 100 and multiply by negative 1. That gives me a mean value of 106.72. So correct interpretation would look like this. His average first serve speed is about 107 miles per hour. You could round that to 107. That's fine. Or you could leave the decimals. It's fine also. Doesn't matter which way you want to go with that. But you do need to show the work and have all the steps included.